In this video, I'm going to be going over the physics behind the conical pendulum and banked corners. And I recommend that as I work through the ideas in this video that you take your own notes, and as I go through the worked examples, you work through them as I do, and then check your working as I go through the steps. You can pause the video in between steps. Okay, so here we go. The objectives for this video is to analyze the forces involved in a conical pendulum, to solve conical pendulum problems, to analyze the forces involved in banked corners, and to solve problems involving banked corners. Alright, so starting with the conical pendulum. The conical pendulum is an example of horizontal circular motion where we have an object on a mass which is swung from the end of a string in a horizontal circle. If we watch the motion of this thing, we can see that as it swings around in this horizontal circle, the string will sweep out the shape of a cone, which is why it's called a conical pendulum. If we watch this again and we just pause its motion at the right point, I'll just go back a little bit there, we can label in the length and the radius of the circular motion. So this here is called the length of the pendulum. That's the length of the string that we've hung our ball from, and we'll give that the symbol capital L. And this here is the radius of the circular motion, which we'll call little r. And the interesting angle here is the angle that the string makes with the vertical. We'll call that theta. Okay, and we can see now that r is the opposite side of this triangle and L is the hypotenuse. So we can write an equation relating theta, r, and L. Sine theta is equal to r over L, or theta is equal to the inverse sine of r over L. Okay, so now we have a relationship between those three basic quantities. Okay, so the next step is going to be to think about what forces are acting in this situation. So we'll have a look at that now. So we can analyze the forces here too. So let's call this angle here theta. Oops. Let's call this angle here theta. So we can label in these forces. We have a weight force acting vertically downwards on the ball. Call that F subscript G. And we have a tension force acting along the string, which we'll call F subscript T. And note one very key thing here is that the tension force is acting at an angle. If we draw an imagined vertical line here, we can see that this angle here is also theta. I think it's called alternate angles. We have this angle is theta, these two lines are parallel, so that angle will also be theta. Okay, so now that we have this, we can now draw a force vector diagram for this. So I'll just remind you of what those vectors looked like again. That's Fg, and we had a tension force like this. This is now a free body diagram, Ft, and we had an angle here of theta. Okay, so if we draw a vector diagram of these, we have the weight force acting downwards, F subscript G, and we have the tension force acting upwards like this, and now we're adding them tip to tail because we're adding these vectors to find the total force. This angle here is theta. This angle, this vector here we can call Ft. And then this here is the resultant or net force, and we can call that one Fc, because that's the net force is what's causing it to move in a circle. That's going to be the centripetal force. So the key to getting to this diagram is to recognize that the tension force plus the weight force must add together to produce a horizontal force, which means in other words that the tension force must have a vertical component that's equal to the weight force, and it must have a horizontal component that's equal to the centripetal force. Okay, so the last step in this analysis then is that we can label the force vector diagram with the equations that we know. Let's draw that again. So it looked like this. We had Fg, Ft, we had an angle here of theta, and so this one is mg, and the centripetal force here, the force that's causing it to move in a circle, is Fc, and that's going to be equal to mv squared, squared over r. Okay. Now, so now our triangle looks like this, where this is mv squared over r, and this is mg, and this is theta. So now we see we have, and this one is ft, which we don't know yet what it is. These two sides here are related to the angle because this is the opposite side. This is here, this one's opposite, and this one is the adjacent side. Whoops, this one is the adjacent side. Okay, and we know that opposite over adjacent should be equal to tan theta. So tan theta must be equal to mv squared over r divided by mg. Well, we can see that when we divide mv squared by mg, the m's cancel, and so this is equal to v squared over rg. So we now have an equation that relates the angle that the string makes with the vertical to the speed at which the object is moving in a circle and the radius of the circle that it's moving in. So we're now equipped to solve problems involving conical pendulums. Let's have a look at how we can apply all of this thinking. So we have a mass hanging from a string of length 1 meter, and it's swung in a circle of radius 0.5 meters. And we are asked to find its speed. So let's just draw that situation. We have a mass hanging like this, and the length here, L, is equal to 1.0 meters, and it's swinging in a circle like this, and the radius here, R, is equal to 0.5 meters. And we can draw a vertical line here, and we can call this angle here theta. Okay, so now the first job in solving any problem involving conical pendulums is usually to figure out the angle, unless the angle is what we're asked for, in which case we would need to work backwards to find it. Okay, so we know that the angle, well, sine theta is going to be equal to r over L. So theta is going to be equal to the inverse sine of 0.5 over 1, which we can figure out. 0.5 divided by 1, which is obviously 0.5, and then we can take the inverse sine of that, and we get 30 degrees. So theta is going to be 30 degrees in this case. Alright, then the next step is to draw a force diagram and a vector diagram. So the force diagram looks like this, where we have our two forces acting. We have Ft and the weight force Fg, which means that our vector diagram will look like this. We'll have the vertical one, which is size mg. This one here is going to be the tension force, Ft, and the net force here, F net, is going to be the centripetal force, so that's mv squared over r. Okay, and we'll call this diagram 1, 2, and 3. So from 3 we see that, and this angle here is theta as well, that tan theta is equal to mv squared over r divided by mg. So tan theta is going to be equal to v squared over rg, which means that v, well, we can rearrange this. We get rg tan theta is equal to v squared. So v is equal to the square root of rg tan theta, which is going to be equal to the square root of 0.5 times 9.81 times the tan of 30, which we can calculate. 0.5 times 9.81 times the tan of 30 equals, and then we'll take the square root of that and we get 1.68 equals 1.7 meters per second, and that's 2 significant figures. Okay, so using the geometry of the situation and our analysis of the forces, we can figure out how fast a conical pendulum would go if its radius is 0.5 and its length is 1 meter. It depends only on the radius and the length. Okay, so our next step in this is to find the period of that same pendulum. Okay, so period and speed are related by this equation. V is equal to 2 pi r, which is the circumference of the circle, and the time that it takes for it to go around the circumference is what we call the period, which is capital T. So to find the period here, we're going to have to go T is equal to 2 pi r over V, which is 2 pi times, and the radius of the circle was 0.5, so that's how far it goes in one full cycle. And the speed that it was going at was rounded to 1.7, but we'll use a less rounded number in our calculation. So it's 1.6828. 1.6828, which gives us an answer of 2 times pi times 0.5 divided by 1.6828 is 1.866. 1.866 seconds, which is roughly equal to 1.9 seconds to 2 significant figures. Okay, so we can also determine the period of the conical pendulum. So using the same approach, we would be able to find any of the unknown quantities if we were asked for them. There are a few other examples in your assignment that will allow you to look at it from a slightly different angle. Okay, the next example, which involves the same physics really, but which involves slightly different forces, is what we call a banked corner. And what we often do, if a corner is going to be one where you have to take it at reasonably high speed and the corner is kind of narrow, we can make it safer by angling the road so that it's angled at the horizontal. And that means that the support force will have a horizontal component, which provides a centripetal force. And if the corner is banked at just the right angle for a given speed and radius, the car can get around the corner with no friction whatsoever. So I'll just show you what I mean by banking here by showing you this short video. So we can see here that the car is moving in a circle. Oops, let me just get rid of that. we have a weight force acting and a normal reaction force, which they've labeled N. That's what we would call the support force. And the combination of those two produces a net force that acts towards the middle of the circle. So it's really the horizontal component of the normal reaction that's producing that. We'll watch the rest of the video because it's going to show us it from a couple of different angles. So here we have the car moving in a circle. It's the combination of the weight force and the net force and the normal reaction force that are producing that net force towards the middle. In other words, the centripetal force. Okay. So that's the analysis that we're gonna go through now. So in order to solve these problems, we start by labeling the forces on the car in the diagram. So we'll have a weight force acting downwards like this, Fg, and we'll have a support force at an angle like this, F support. And the angle here, the angle of banking is usually quoted as this angle, theta. But that angle will be the same. Oops, let me just get rid of that. And draw a vertical here. This angle here will also be theta. And that's kind of, if you think of the road, if you rotate it by an angle theta, then the normal reaction force will also be rotated by the same angle theta from the vertical, because the normal reaction force or support force is always perpendicular to the ground. Okay. So now we can do a little analysis of these forces. So I'll just relabel those two vectors here. We have the Fg and we have F support here. And we can draw the net force that they produce like this, Fg and F support. And because the car is moving in a horizontal circle, we know that the net force must be towards the center of the circle like this. And that net force is going to be equal to the centripetal force. Let me just go back to that for a second. So here we have, and then also this angle here is the angle of banking. So that's this angle here, which is the same as that angle there. Okay, so now we can note that the weight force, if we draw that diagram again, this weight force here is mg, where m is the mass of the car, and the support force looks like this, F support, and there's our angle, and this is our centripetal force, which has the equation mv squared over r. So this is looking very similar to what we had for the conical pendulum, where the tan of the angle is going to be equal to mv squared over r divided by mg. So if we cancel these m's, we can see that we get v squared over rg again. And so now we have an expression that relates the angle of banking to the speed, the radius of the corner that the car is turning, and the acceleration due to gravity. Okay, so just to go through an example of where we might apply this. So we have a motorway off-ramp, and the cars turn a corner of radius 90 meters at a speed of 80 kilometers per hour, which is 22 meters per second. At what angle should the road be angled so that the cars could take the corner without relying on friction to provide the centripetal force? So, in other words, what we want is the banking to produce a force that is equal to the centripetal force that the car needs. So let's label in the two forces. This is Fg, and then we have F support perpendicular to the road. We have here an angle that we're trying to find, and that will also be this angle that the support force makes with the vertical, call that theta. And then we'll draw a vector diagram of that so that we have a clear sense of what's going on. So we have a downwards weight force, which is equal to mg. We have a support force like this. Sorry, I should really draw it at a similar sort of angle. Support force like this, F support. And we have this force here, which we want to be equal to mv squared over r. Right. And this is theta. Okay. Now, the first thing that we'll do is we'll just rearrange that symbolically, and then we'll put in the numbers that we want and rearrange it for theta, which is what we're trying to find out. So we know that tan theta must be equal to mv squared over r divided by mg. So in other words, that's going to be equal to v squared over rg. Okay, and we know what v is, it's 22 meters per second. We know that what r is, it's 90 meters. And obviously we know what g is. We're wanting to find theta, so let's just take the inverse tan of both sides, and we find that theta is going to be equal to the inverse tan of v squared over rg, which is equal to the inverse tan of v, which is 22 squared, over 90 times 9.81. And we find that the ideal angle of banking is, we want to remove that, and we want 22 squared divided by 90 times 9.81, and then all of that we want to take the inverse tan of, which gives us an angle of 28.7 degrees. .7 degrees, or 29 degrees to two significant figures. It should be to two significant figures because all of our data here was given to 2. Okay, so that's an example of how we can use the equations that we've derived to solve problems involving banked corners. There are a number of other examples of banked corners that we should just be familiar with. Planes bank when they are turning. So by banking with planes, we mean basically that they angle themselves to the horizontal so that the lift force is at an angle. So here we'd have a weight force, Fg, and we'd have a lift force like this, Fl. And when we add those, we'll get a horizontal force. So the vector diagram would look like this, and we'd end up with a horizontal force this way, which would provide the centripetal force acting towards the center, Fl, acting towards the center of the circular path that plane would be following. Similarly, a bobsled, that's very similar to the car, where we have a weight force acting downwards and we'd have a support force acting vertically up from the surface. And for a cyclist on a velodrome, we can see that he's angled quite sharply. He'd have a weight force acting downwards, and he'd have a support force acting up from the track, like that. And a snowboarder rounding a banked corner as well, he would have a weight force acting downwards on him like this, and he'd have an angled support force acting like this. And that would allow him to get around this corner more easily. So in all of those situations, basically we have two forces combining. One is the weight force, and the other is an angled upwards force. When we add those together, we will always get a triangle that looks something like this. where the downwards vertical one is the weight force, and the angled one is either the support or the lift force. And we then end up with a net force that's towards the middle that's going to provide the centripetal force. To explain banked corners, basically, as the car goes around the corner, the vector sum of the weight force, maybe I shouldn't be using red here, I'll just change to green. The vector sum of the weight force and the support force produce a net force towards the center of the circle, which acts as a centripetal force, keeping the car moving in a circle. Okay, so just to summarize what we've gone through in this video, conical pendulums and banked corners are examples where the centripetal force is provided by the vector sum of two forces acting on the object. For a conical pendulum, the centripetal force is provided by the vector sum of the weight force and the tension force. The angle that the string makes with the vertical is also the angle that the tension force makes with the vertical. By drawing a force vector diagram, we can deduce that tan theta will be equal to v squared over gr. Similarly, for a car on a banked corner, the vector sum of the weight and the support results in a net force towards the center of the circle. Again, by drawing a force diagram, we can deduce that tan theta is equal to v squared over gr. And that's the end of this particular video. Obviously, in order to reinforce those concepts, you're going to need to complete the assignment and do some of the practice problems that are suggested.